Lesson 7, Analyzing Bubblesort. In this video, we will give a careful time complexity analysis of the Bubblesort algorithm using the definition of big theta that we gave previously. This is intended to be a thorough algorithmic analysis. In the future analyses, we will skip many of the basic steps that we cover here. Our complexity analysis will determine how the number of algorithm steps varies with respect to the number of entries that are sorted. For our purposes, we are assuming that the entries that we are sorting are in an array. Here's the C++ code for the Bubblesort algorithm. The array that this sorts is IA array, which in this case has size in. The outer for loop is indexed by the last unsorted element. Notice that this loop runs from in-1 to 0, so that when it is done, the array is sorted. The inner loop runs from the first entry to the entry before the last unsorted element, and this loop sends the next highest element to the position last. Inside the loop, we compare the entries at icomp to the one after it, and swap them if they are out of order. Notice that the code inside the loops does not depend on in. Since this code is constant with respect to the size of the array, we can consider it all as a single block and ask how many times it is executed. Now we're going to do our analysis and leave the code behind, so I will switch to small n instead of in to use more traditional mathematical notation. The outer loop executes n-1 times, and the inner loop executes n-1 times, then n-2 times, and so on down to 1, corresponding to each outer loop. So the inner code is executed a total of n-1 plus n-2 plus n-3 down to 1 times. This sums to n-1 times n divided by 2, or n squared divided by 2 minus n divided by 2. Recall the definitions from our previous lesson on complexity analysis. In this case, f of n is n squared divided by 2 minus n divided by 2. The function g of n is n squared since we want g of n to be a simpler function and n squared dominates n for large values of n. Now in order to show that the algorithm is big theta of n squared, we need to find positive constants c1 and c2 and a positive integer n0 such that c1 times g of n is greater than or equal to f of n, which is greater than or equal to c2 times g of n, or c1 times n squared is greater than or equal to n squared divided by 2 minus n divided by 2, which is greater than or equal to c2 times n squared for all values of n greater than or equal to n0. Since our coefficient is 1/2 on the n squared term for f of n, any value of c1 greater than or equal to 1/2 and any value of c2 less than 1/2 will work to demonstrate that the Bubblesort is big theta of n squared. For simplicity, we choose c1 equals 1 and c2 equals 1/4. Here's a table of the first few values for each function. Notice that any value of n greater than or equal to 2 appears to satisfy our inequalities, so we choose n0 equal 2. Even though n0 equals 2 appears to work, we still need to prove that our conditions are true. That is, we need to show that c1 times g of n is greater than or equal to f of n, and f of n is greater than or equal to c2 times g of n for all n greater than or equal to 2. We proved this by induction. To do this, we observe that the inequalities hold for n equals 2. Then we want to show that if the inequalities hold for the case n equals k, where k is greater than or equal to 2, then they hold for the k plus 1 case as well. This will allow us to say that the 2 case implies the 3 case, which in turn implies the 4 case, and so on. We begin with the first inequality. We need to show that c1 times g of k plus 1 is greater than or equal to f of k plus 1. We begin with the left side, making a substitution of 1 for c1 and k plus 1 squared for g of k plus 1 gives us this. Expanding, we get k squared plus 2k plus 1. In the next line, we observe that the k squared is simply c1 times g of k. Using the inequality for the kth case, we get this. A substitution for f of k and some simplification gives us this. This next line follows from the fact that k over 2 is less than 3k over 2 plus 1. We finish the proof by substituting f of k plus 1 for k squared over 2 plus k over 2, which is what it equals. Now let's move on to the second inequality. We need to show that c2 times g of k plus 1 is less than or equal to f of k plus 1. We start with the left side and make our substitutions for c2 and g of k plus 1 to get this. Next, we expand the product to get this. And then we replace 1/4 k squared with c2 times g of k. Using our inequality for the kth case, we get this, which equals this by substitution and simplification. The next inequality follows from the fact that 1/4 is less than k over 2 for all k greater than or equal to 2. Of course, k squared over 2 plus k over 2 is just the value of f of k plus 1. So we are done, and that finishes off the proof that the bubble sort algorithm is big theta of n squared.